Hello, everyone. We're very excited to welcome you all to the 14th VisiMix webinar. The focus of today's webinar will be VisiMix Chem and the fourth Bourne reaction system, how VisiMix Chem predicts the impact of mixing on fast, sensitive, competing chemical reactions in stirred tank reactors, and comparing the predictions with experimental results published in Chemical Engineering Science in 2005. We're very delighted to introduce our guest speaker, Dr. Reinaldo Ray Machado. Ray has 40 years of expertise in chemical engineering, specializing in scale-up techniques and reactor engineering. Ray is a consultant, adjunct faculty, and 24 patent holder with vast insights that bridge industry and academia. Ray is very passionate about turning lab innovations into real-world impact across the pharmaceutical, specialty, and electronics industries. If you have any questions during the course of this session, please feel free to write them in the chat box. We will do our best to address them during the session or afterwards via email. So without any further ado, I'll pass the microphone over to Dr. Machado. Ray, the microphone is all yours.
Yes. From Arizona. Thank you, guys. Okay. My apologies here. Something came up for asking for new hardware. I do not know. Anyway, it was very strange. Acid-base reactions are very fast. We all know of very fast processes, especially things like oxidations. I'm sure you guys know a lot more. Nitrations are big problems. Thermal decompositions. There are many fast reactions which occur. This becomes very problematic when there's competitive processes that generate really unwanted products. The problems occur when there's local concentration gradients and the materials are not homogeneous. And what I mean by homogeneous is that things that do not occur instantaneously at a molecular level. In fact, mixing is best when our molecules are equally dispersed at a molecular scale before any significant reactions take place. This is really our goal. Unfortunately, real systems take time. I wanted to show you just a quick video here. This is a very simple reaction where I'm adding iodines to sodium thiosulfate, and what we can see is the yellow iodine, and the iodine can react with starch if it doesn't react instantaneously with the thiosulfate. So let this process begin. And what we see here now is you'll see very quickly I've put in a chart the maximum difference in concentration based upon the VisiMix calculations. And what you can see on the left-hand side is 200 RPMs, the right-hand side is 800 RPMs. And as time goes by, we see that the greater concentration gradients are occurring at the lower RPM levels. And this is pretty obvious and visually can be seen here. These videos come from my mixing laboratory, which I use to characterize processes and look at them. As we get toward the end of the reaction, we're getting close to the final stoichiometry, and what we see is the very strong gradients on the left-hand side. This is just a summary in visual picture here that shows as we go from 6 seconds of addition to 42 seconds when we end the feed and get very close to our stoichiometric level, we see a very long gradients of the material from the feed tube. If we take a look at comparing the 200 and the 800 RPMs, I just wanted you to visualize what can happen as we change our agitation rates, and what actually changes is the actual location of the reaction and whether it's occurring in a micro mixing scale or a macro mixing scale. These really depend very strongly on the RPM rate. And there's a transition that often occurs. Early on, what you'll see is that everything appears to be very similar, but later on we see the greater discrepancy as the kinetics slow down. I wanted to share with you a class of mixing sensitive chemical reaction recipe well known as the Bourne's fourth reaction. Dr. John Bourne is well known for his studies in fast reaction chemistry and the impact of mixing on chemical reaction processes. And this process, let me walk you through it, was studied by a team out in New Jersey, which took a look at using this chemical reaction recipe to characterize their laboratory reactors. There are two critical reactions that occur. Let me describe them to you first. The first into the reactor is HCl and ethyl chloroacetate, and to the reactor, sodium hydroxide is added. As you know, the reaction of sodium chloride, hydrogen chloride, HCl, and sodium hydroxide is a very fast reaction. We'll call that lightning speed, basically molecular diffusion controlled. The reaction with the ethyl chloroacetate is also very fast, not quite as lightning fast, but still incredibly fast. And this we're going to consider in this reaction sequence to be our undesired reaction that's very fast. We prefer to have everything go to sodium chloride, but as the reaction mixing is incomplete, we'll see the presence of the ethanol, and that it really represents the byproduct chemistry. And that selectivity of the byproduct is calculated from the concentration of ethanol over ethanol plus sodium chloride. If we take a look at this is how the reactor is set up, sodium hydroxide is added into the reaction are equal molar amounts of hydrochloric acid and ethyl chloroacetate. In this particular example that was done by our team in New Jersey, they used 0.05 moles of HCl and ethyl chloroacetate, and then they added sodium hydroxide over 20 minutes to match the stoichiometric quantities. The overall ratios of the hydroxide to the acid were 1:1. And so the question is, what is the hydroxide preferentially reacting to? If you wind up with a selectivity of 0, that means you've got a perfectly mixed reactor, that the ethyl chloroacetate just cannot compete with the HCl. And so what you wind up with is a selectivity to ethanol that is basically 0. But on the other hand, if you have a completely segregated reactor and that there's equal opportunity for the ethyl chloroacetate and HCl to react, then you wind up with a selectivity of 0.5. Keep this in mind as we go forward. This is the paper that was done. This just gives you some illustrations of the reactors and the agitators that were used. I wanted to make a simple point. This impeller, which they call an anchor impeller, is really more like a paddle impeller. And so after some hydraulic analysis and using VisiMix, and sometimes, as you know, we have to accommodate various approximations that allow us then to put the data into the VisiMix system, VisiMix software. These were the parameters that were studied. There were 20 reactions that were done. They used different types of impeller agitation, 100, 300, and 500. There were different impellers, a 30-degree pitch blade turbine, a 45-degree pitch blade turbine. They put the feed at different locations above the liquid, 90% of the fill level, and above the impeller. Sometimes they had 0, 1, or 2 baffles, and different fill levels in these reactors. Now this is a bit of an eye chart, and I wanted just to show you the parameters that were used, the 20 reactions that were done. And I wanted to point out one other thing too. Reaction number 16 was always problematic in all the analysis. I tried to find out whether or not that reaction was not recorded properly. I contacted the authors of the paper. I did not get a clear response to that, so I've kind of left experiment number run 16 off so that I could make sense of all the information that we got. And this was the experiments with a distribution of all these reactions. Now, this is also an eye chart, but I don't want you to be discouraged, because what I wanted to point out here is I characterized all kinds of things. So in this part of the analysis, I'm going to go through just very quickly. If you look at the top left-hand side for the different agitation rates, I looked at the maximum differential of the components for an instantaneous reaction. I looked at the average of the maximum differential. I looked at the power. I looked at the average power. I looked at the power at the feed point. I looked at the micro mixing, the macro mixing times, the circulation rates, et cetera, et cetera. One of the things that I really like to do is use the VisiMix to calculate, for example, at an instantaneous reaction, what is the maximum differential for the ingredients in the reactor? And this gives us a lot of insight as to how materials are being either homogeneously mixed or perhaps less homogeneously mixed. And as you can see at the low agitation power levels of 2.54 watts per kilogram, I see a pretty wide distribution of the HCl. Whereas when you increase the power level to 4.6 watts per kilogram, I see the differential in the HCl to be far reduced. And you see a more homogeneous mixture as you increase the power level, as you would suspect. And also, if you take a look, the selectivity here was, for the left-hand side, was 11%, 0.114, and at the right-hand side, it was about half that much with twice the power. Now, one of the other things I like to do is plot things different ways. And so, whoops, excuse me. So in this particular case, what I did was I took a look at the experimental selectivities, and I just put all the information on the concentration gradient for hydrochloric acid. And I also took a look at the energy dissipation and the impact that had on the selectivity. I want to point out that 0.5 is our stoichiometric limit for the completely segregated reactor. You'll see a reasonable correlation just with the gradient or with the power. But I want to point out something also very interesting. If you look at the correlation on the left, what you'll see using a power law correlation is that there's a slope of approximately 1/2, as the experimental selectivity over this region is approximately the concentration gradient to the 1/2 power. We'll bring this up a little bit later as we analyze the data. Now, another paper that I'm very fond of that I've used consistently over my career is one done by Professor Forney at the Georgia Institute of Technology. And what he's able to do is he actually divides the selectivity of this particular reaction into two parts. One is a micro mixing part, which is on the left-hand side of the correlation, and then one is what they call a meso mixing or inertial scale part on the right-hand side. Now, it turns out that all the experiments that were done in the previous studies where I had all the data were done in the micro mixing regime. And as you see, there's a correlation that shows the kinetics divided by the energy. Let's take a look at this. So in Dr. Forney's approach, he takes a look at a laminar flow that is elongated along the agitation zone, and he describes it accordingly. You can pull the paper up yourself. We can talk about it later. I teach this in my short course as we look at this, but it really is one of the ways to look at how material is distributed in a reactor. Now, what you'll notice is this is the results that he got. You'll see the left-hand side is the micro mixing regime. The right-hand side is the inertial meso mixing regime. And I want to take a look at that and see how the data from the previous study compares. And as you can see, it's a very good comparison. Now let's take a look at the left-hand side and the right-hand side, which are really on the same scales. And what allows all that data to fit so nicely is basically using my estimates from VisiMix. So I do this very, very often, where I use VisiMix to do my calculations for the local energy dissipations, and I use that in other correlations to find out how it works. And as you can see, it works quite well. And in these charts, as you increase your mixing intensity, you're going from the right-hand side to the left, and the decreasing byproduct ethanol is going down. So our goal is to have the lowest possible Damkohler number. Recall from the previous slide that Damkohler number is the relationship between the kinetics rates divided by the mixing rates. But I want you to notice something else which is quite fascinating. Look at this. The slope in this region is approximately 1/2 in this micro mixing region. Guess what? That's exactly what we discovered in the differential HCl average concentrations from the VisiMix calculations. And this is consistent with what you would expect to find. As we know, VisiMix allows us to do some really nice work to understand, for example, how material is distributed. I think this is a video that people have seen many times before, where you can use your VisiMix calculations to understand how material is moving throughout a reactor. And what's interesting is that this gave rise to the use of VisiMix Chem, which then calculates local concentrations in the reactor. VisiMix Chem, I was pushing this to the limits. In other words, this is the chemistry from the study that we saw. We see the initial concentrations in the tank at 0.05 moles per liter. We see our sodium hydroxide is at 1 mole per liter. That is our feed. And I think if you've used VisiMix Chem, you've seen that. And when I say I pushed it to the limits, I'm really putting in some really fast reactions, and here's what I mean. So the neutralization reaction, as you can imagine, is 10 to the 11th power. That's pretty fast. And even our hydrolysis of the ethyl chloroacetate with sodium hydroxide is extremely fast. Now, originally, when I was looking at VisiMix Chem, I actually put in a lower reaction rate, which I had to go back and check, and found out, no, it's 23 and not 2.3, which changed some of my initial results, obviously. What's nice about the VisiMix Chem is that you set up your reactors in a very similar way to using standard VisiMix. As we can see here, for the reactors, I chose for this as one of the conditions where I had 170 mLs, 1,700 mLs. We had we had one baffle in that particular reactor. The impeller at this point was a pitch blade paddle at 30 degrees. It was in the process location was about 90% of the liquid height, as you can see from feed 1. They really didn't use feed 2. My addition rate was 0.055 liters per hour. And these are some of the results that we achieved in that reaction. So here we see the HCl concentration, the conversion increasing, and we also see the conversion of the ethyl chloroacetate. Of course, now let's compare it to the data. Oh, of course, I wanted to also mention we get our distinctive calculations for the concentrations and also for the HCl concentrations, and also the conversions. Now, here we go. So what we see in the green is the experimental results, as I just is presenting it as the maximum energy dissipation, and we see in red the VisiMix calculations. Not quite in complete agreement. Now, the ethanol here is a little bit over predicted, and the selectivities approach more of a segregated flow at a lower intensity. And the VisiMix Chem is really conservative for these extremely fast reactions, at least the ones I chose. So originally, when I was doing this, I had accidentally put in a lower level of kinetics, and I got them to agree much more closely. However, I did review the literature, I updated my kinetics, and you can see that the agreement is not as as consistent as we'd like. Nevertheless, the trends are important, and that is, as we increase our maximum dissipation, we see that our selectivity to the impurity decreases, which is what we would expect. And then here's another look at the data where I put it in terms of the correlations from the paper by Forney, and the red represents the VisiMix calculations getting closer to the segregated flow. But nevertheless, we see as we move to mixing intensity, we see that the which lower Damkohler numbers, we see that the selectivity does improve, or it gets lower for the impurity. The trends are useful, though, for understanding the impact of these variables. So we shouldn't just dismiss things that don't match perfectly. Here I just took a look at using the VisiMix Chem for different concentrations and different RPMs for the previous example. And as you can see, as you increase the agitation rate, we see a very large decline in the overall selectivity of the impurity, which we do want to go down. And that is impacted both by the concentration of the sodium hydroxide as well as the agitation rate. And this is just some of the calculations that you can do to look at the various trends in the process. And I think I've perhaps gone too fast in being overly anxious about the timing, and I am very sorry about that. There apparently was some impact of the software trying to find new hardware, and it happens. So we can assume that mixing is important in your process. I never have a situation where I automatically dismiss mixing. I do my overall calculations to see what's going on. I practice really very diverse strategies with VisiMix, as I showed earlier. One, I characterize all my zones of energy dissipation, flow, shear, and velocities, make sure I understand what is changing under what conditions. I always evaluate my micro and macro mixing trends. I use different values to see which way it's going and how it impacts the overall process. I estimate my concentration gradients for the simplified chemistries. So by just simply assuming an instantaneous chemistry, you can get an understanding of the degree of homogeneity within your reactor. And this is really cool because it allows you then to get some handle on how dispersed materials really are. I then build some VisiMix Chem models and I test various sensitivities. And I identify the trends from these models. And I always remember something my dad told me, and it's a rule I live by. It doesn't have to be perfect to be helpful and to guide us in the right directions. I wanted to say something else. Thinking, sharing, discussing. So I think about what I'm doing, I share it with my colleagues, we discuss it, I recycle back, and when we do this, we generate new knowledge, and of course we know that new knowledge can lead to opportunities for inventions, opportunities for optimization of processes, etc., and allows us really to convert that information into knowledge, and then eventually into money that impacts our companies. I remember some very important principles of the scientific method, and this drives my understanding all the time. I compare the data, I compare the measurements, I compare the theories, I compare the models. The big benefit, I have to say, for using VisiMix overall is that you can do things quickly. You can get many evaluations over a very short period of time. Why that's important? Time is important. If you lag by waiting for a day or two for a CFD model, or for getting to get all the different potential combinations and permutations that you would like to see, it will take forever. A good analysis for the 20 reactions that I did took really less than one morning. So that is really how important VisiMix is in its tool to determine how hydraulics and mixing affect your overall process chemistry. I always remember that to succeed, we want to work smart, we want to work efficiently, which is why VisiMix is so good. We want to seek the best team on day one. That's another very important thing. Engineers working with chemists, chemists working with engineers at the beginning to try to understand the important aspects of your process and to anticipate problems by using tools like VisiMix and all the other things that come to play, so that basically on day one, you're thinking in the right direction. As we know, things currently go in such a rapid timing in so many of our industries, electronics, pharmaceuticals, that we really want to start with the best foot forward. I know we can always recycle back, but it's so much easier to start with the best team on day one. Never give up. I don't give up. I keep moving forward. I keep finding the obstacles and overcoming them. And I question everything. I'm always looking back, always going back to the fundamentals, going back to the original literature articles to make sure there wasn't a typographical error which can really mess you up. I want to remember, mix all these ideas together, and that will be one of your best ways of moving forward. From that, and once again, I want to apologize for this unusual difficulty getting my audio working. I upgraded just recently my Microsoft, and now it's constantly asking for questions, and I think the AI has taken over my computer. Anyway, I want to thank you for your time, and I apologize for the audio problems. And I want to especially thank VisiMix for their great support over many years. I've been using them since the 1990s. Their useful software has always been a key aspect of my success at my companies, at Air Products, at Versum and EMD Electronics as a part of Merck, Darmstadt, Germany. Wonderful training. I can't give you great videos online. A real can-do attitude, always willing to work with you, and real friendship, and I mean that from my heart. I have a lot of things that I'd like to share. If you're interested in a short course, you can just take a look at my my website, get some insight, give me a call. Be glad to come to your company. I will talk about many different things from VisiMix and from how to do reactions and kinetics and how to design new experiments in really crazy, unique ways, how to get lots of knowledge very quickly, and hopefully that could be of some use to you. So with that, I'll hand it over, Moshe.
Yes.
I got it done.
Thank you very much. It was very interesting. And I have here a question for you from Cliff Cowell, that we know him well. I'm happy to see you here, Cliff. His question is, did you consider scaling up impact on the modeling? Not only here in VisiMix Chem, you can discuss about VisiMix scale-up activities maybe you use.
Yes, yeah. So I have used it a lot. I did scale this particular reaction up. Okay, I went to the larger scale vessels, and I found the same sorts of impacts, changing concentration, improving the agitation. And what I discovered, okay, as you wouldn't be surprised, because the level of agitation energy was less at the scale-up conditions, what you see is you get very close to what's called segregated flow, where basically you wind up with very poor selectivity in this particular reaction. This reaction is a tough one if you were going to scale it up for real. I have rarely run into reactions that are quite that fast and under the mixing zone. And what I found out is that when you do the scale up of reactions that are still very fast, but not quite this fast, you can see a lot more reasonable scale up effects. So yes, I have used this quite extensively. The largest scale up I have done with VisiMix is for 15 cubic meters for high intensity three-phase hydrogenation reactions. And we've been very successful at getting very, very good scale up for those levels, to 15 cubic meters, high pressure vessels doing very fast hydrogenations.
Very good. I have a question. If you can come back to the slide that you showed, the power half, the concentration. There, I want to ask, even here when you put when you discover that it is the same power, it is enough. My question here is, when you achieve the power half, okay?
Yeah.
You got from your empirical data, yes?
Yeah.
And after that, you came to Dr. Forney paper.
Yes.
And he wrote here this power. And he finds some way to calculate the relationship between the maximum energy expression and the energy expression in the feed. Okay, I don't know how he did it. Okay? But my question is, why he is coming to half, to power half? Is something that he did by correlation to, or is something that he came with some combination or mathematical development?
Okay, so he does a mathematical development, and all he did was plot the data for many reactions on this paper. And so the only thing he contributed to the work is he took a look at this Damkohler number you see below, and I can go into more detail of how he calculates it. He takes all the data that's available and he plots it according to that Damkohler number. And that Damkohler number is based upon a laminar feed into the reactor. Now, the reason he looked at this system is he wanted to know under what conditions do you have laminar feed, what does it do? And all the laboratory studies that I can tell from my calculations all have laminar feeds into their reactor, okay? In other words, it doesn't correlate to a turbulent feed into a reactor, which is a very different type of feed situation. But I just plotted it because the laboratory data that was done in this study I'm talking about most likely was under laminar flow conditions. And then when you look at that, this is what you wind up getting. So I find this, and I do have a question mark here because I need to do further investigation, but this is the type of correlation I look for as I look into data. You know, what are these relationships? But that data there is just purely a plot of the existing data. And that bottom Damkohler number is when he calculated. Now, I will show you one other thing if we go further. You know, one of the things that I go into in my short course is I take a look at different types of feeds under what are called cross flow and turbulent feed additions. And these give different types of results when you're feeding, especially if you're dropping from a high altitude into your reactor from a very high region. You have to calculate what's going on, what's the impact of the momentum, and I look at that for different types of feed conditions, depending upon whether you have momentum transfer. And so, you know, that just depends upon the scale of the reactor. Yeah.
And when you show us that you calculate the maximum energy expression divided by the feeding, this was in the place that you are feeding, yes? Okay, so
yes.
those energy expression you calculate in the tank, yes?
Yes. Yes.
So even the flow is laminar, the surrounding of the tank maybe is not laminar. Yes.
Yeah. Well, so that's what I wanted to see. You know, so I only am showing this because of the is it a coincidence or is there something more to it? And it only says that it enters in a laminar way. Yeah, that's just the way Forney looks at the data. I mean, I don't have any other explanation.
Yeah, but you can see that with two different empirical and some kind of semi-empirical model like VisiMix, you are able to get a similar number. The meaning of this that you can, let's say, confirm yourself that the theory or the phenomena that happened behind it it is able to reproduce by calculation. This is what we can get from it.
Yeah. Yeah.
Perfect.
So yeah, and I wanted to point this out to everyone listening in. So another lesson that I have is, as you can see, I'm bringing different literature articles. In fact, I have many more than this that I brought to bear on this particular reaction sequence, and I look at them from many different directions, and I use all the tools available, the modeling tools, the data, the correlations, and I'm looking for information that will help me to advance my knowledge, and this was just one that I did. I think equally as important on the right-hand side of this, you'll see that I'm using my VisiMix data, putting it into this correlation, and getting a very nice fit to the empirical relationship that Dr.
Yes.
Ford has developed.
Here is a very important point, because when we talk about any process, it is not only for reactions. It can be for any kind of operations that we are doing in our process, like crystallization and other. Normally, you have some starting point model and idea that try to describe the process, like crystallization, for instance. And sometimes the mixing consideration there is very basic level. And when you go to a little more level, like you did now here, and it can be in many other kinds of activities, and you use the basic, but a little more sophisticated, like try to see where you fit, what is the energy there, and more. You can find by calculations the influence of the mixing the process, at least the influence, at least some trend, and that guiding you to come to the final decision or final experiments you need to perform in order to prove that what you are thinking is correct.
Yes, yes,
we are
absolutely.
dealing on it. In VisiMix, we are trying to go to this step, to try to come from theories of crystallization that are now a little better according to our customers, and try to generate some input data into the general theories in order to try to by using VisiMix to give our customer more knowledge directly to the particle size distribution and more. You know, we did it in the emulsification, two phases that are not miscible. I want to do in more activities, so it's very interesting thing to do, or how to estimate the feeding position, the diameter of the feeding position, and more. It is very interesting. And another one point we want to invite our audience here, of course, is to contact us for any question you have about VisiMix. And another point that we are working hardly with Dr. Machado in order to generate some kind of training, more than training, some kind of guidelines how to work in Scala, how to do some kind of tools for Scala, let's say school of Scala, and we're trying to generate this during the next year. So follow our announcements. We'll try to do it, and we'll try to combine all the knowledge that coming from Dr. Machado, all the knowledge coming from VisiMix staff, and to try to provide to you not only some theories separate from some calculations, separate some how to design the experiment. We'll try to provide to you a training that will cover all, integrate in order to guide your people in the industry and companies to have an integration of all in order to give a tool for this kind of activities. So if you are doing some kind of, come to VisiMix and know about how to model it. Come to Dr. Machado and know how to have some fundamentals of scale-up. We'll try to do together and to do it in the lab, to show to you how to set up in the lab and to generate results and guide you how to go to scale-up. Is something that we're working on, and we hope we will try to release during the next year. Ray, do you want to add something more about it?
No, I think this is great, and I just can't overemphasize the need to work as teams, to keep thinking, and don't just use any calculation tool as the only thing. You got to just, it's what I call I'm trying to take us to the next level. Rather than AI, I'm trying to take us to HI, which is human intelligence,
Yes.
and working as a team. It's a
It's
lot
more,
more fun.
yeah, yes, more sensitive and more live than only some collection of information that very smart, but continue to be collection of information that is exists and want to put our mind in order to generate the next the next step. That will be, of course, a combination of what we know, our intuition, and all the theories that are available for us. Okay, so thank you very much. It was not at the beginning. It's okay. It happened always, not always, but it happens from time to time.
Yeah.
But we have here a good audition here. Anyway, for everyone, we will send the presentation. We will send the video. And if you want to see more about VisiMix Chem, you are invited to contact us. We are doing tailored presentation for every company they want. And we're showing the software, showing maybe your data in the software to show to you how you can good direction and be more smart in order to progress to your process. So thank you very much, Ray. Thank you very much for your attention, and looking forward to looking for more to see you again in different VisiMix forum. It was a special one, end of the year. We're celebrating with Ray that we succeeded this year, and we will be able to succeed more next year. Thank you very much for your time. Bye-bye.
Thank you very much, Moshe.